Are you ready to talk about Prentice's rule? We're going to talk about that and more as we continue on with ophthalmic optics. In this video, we're going to talk about Prentice's rule and different ways that we can apply it in prism-related problems. So let's talk about what is Prentice's rule. So you guys all know Prentice's rule, right? Prism equals D times F, right? D being the distance from the optical center, F being the power in that meridian or the power of that lens, right? But what's the one thing about that equation that you could potentially mess up while you're doing problems? Yeah, it's exactly right? That distance from the optical center has got to be in what length? It's got to be in centimeters, right? Remember, we're still in prisms, right? We said in the last video, we're in prism land. Not everything is in meters right now, right? So this is the second in our equations that don't use meters exclusively, right? Is going to be all of prisms, right? And it's specifically Prentice's rule. All right, good. Now we're going to talk about some different uses of Prentice's rule, but different names. So let's take it to the whiteboard. So let's talk about uses of Prentice's rule, but different names. There's going to be 4 of these. So take a second, pause the video, because I think it'll be really helpful for you to have this in your notes out to the side so you can reference this as you move forward, attacking these problems and attacking quiz questions and the SMART test as you guys continue to work and progress towards studying for boards. So the first way we're going to talk about using Prentice's rule, but it's not going to say, hey, use Prentice's rule, right? It's going to be decentration. So any kind of question where it says you decenter a lens, how much prism is going to be induced? Think all I'm doing is Prentice's rule, right? Second way is going to be vertical imbalance. That's going to be 2 eyes, key point, okay? So 2 eyes, right? Vertical imbalance. It's going to be the third way is going to be image jump, right? And that's going to be, all you need to know for image jump is 2 things, add type and add power, right? So we'll get that, we'll run an example of that. The last one's going to be total prismatic effect, okay? And all you need to know there is 1 eye, right? The key point there being 1 eye. So anytime you see any of these 4 in a problem, right? You're going to think, okay, all I know is that I'm doing Prentice's rule at some point in this problem. I can do this. Let's get into decentering. When I think of a plus lens, I like to think of it as being like 2 prisms base to base, right? And whenever I think of a minus lens, I like to think of it as like 2 prisms apex to apex, right? So that way whenever I'm going through a decentering problem or any kind of Prentice's rule problem, I can kind of think my way through, because whenever you think about Prentice's rule, a lot of times it's really easy to be able to calculate the power, right? The prism power, but then, you got the other question that could be, okay, what kind of base direction it would be, right? And that could be like a multiple response type of question that could come up, right? So whenever I'm thinking about that, here's how I draw it. So I know this kind of seems maybe like a little bit kindergartenish, but in every problem I do for Prentice's rule or any kind of prism type of problem, I will draw this out. If it's a plus lens, I'll draw 2 prisms base to base, and if it's a minus lens, 2 prisms apex to apex. So that'll kind of help me understand the problem and try to make sure I get that base direction correct, right? So one of the things that we want to think about is, okay, if I am here, right, and I am looking up in a plus lens, what kind of prism is going to be induced? Yeah, it's going to be base down prism, right? It's going to be base down prism. So that's one way to think about decentering, okay? The other one would be, what about if I was looking straight ahead, but we moved a plus lens up, right? What would happen there? If we moved a plus lens up, right, what kind of prism is going to be induced, right? So if we take that lens and we move it up, right, then it's going to induce base up prism now, right? And so that's one of the ways to conceptually think about this concept, and I think that's going to be really important moving forward. And the same thing could be true for a minus lens, right? If we take and we put our eye over here, right, and we look down in a minus lens, right, what kind of prism is going to be induced, right? If we look down in a minus lens, that's going to induce base down prism, right? And so sometimes if we just think through a question and we try to think conceptually with that question, we can kind of get tripped up. But I think drawing this simple picture will make sure you guys dominate every one of these questions moving forward. Let's keep going, and we're going to work example 5.15, and that's going to illustrate power in the oblique meridian, how that can be used with Prentice's rule. So this example says, find the vertical prism induced in the right eye when a patient looks 10 millimeters below the optical center in the following lens, +2, -150, axis 135. So I've got this on a power cross, right? And just like we did in geometrical optics, we talked about this before, since we're equally divided along the vertical meridian, right? With one meridian being at 45 and the other one being here at 135, right? Then what allow that to do is that we can actually find the power in the vertical meridian of this astigmatic lens without having to use a sine squared rule, right? And so what's going to be that power in the vertical meridian? Yeah, that's exactly right. It's going to be +1.25, right? So +1.25 diopters. Now this is a plus lens, so for me, I'm always going to draw, just like we did a second ago, right? I'm going to draw a prism like this, 2 prisms base to base, right? And that's going to help me be able to think my way through what kind of base direction of prism is going to be induced in this problem. All right, now that we've set this up, I'm going to pause for a second, let you work out the problem to completion, and then we'll come back together again. So to solve this problem, we're going to simply use Prentice's rule, right? And the one catch you have to remember is that you're going to have to convert this 10 millimeters they give you in the problem into centimeters, right? Because remember, with Prentice's rule, we use centimeters, right? So 1.0 centimeters times that 1.25 power on the vertical meridian is going to give us 1.25 diopters. Then the question comes, okay, this may be a pick 2 type of question. What's going to be the base direction, right? The patient is going to be looking down in a plus lens, so they're going to have what kind of prism induced? It's going to be base up prism. I love it, guys. You did great on that problem. All right, let's talk about another way to kind of stretch Prentice's rule. So check this out. What happens if we have decentration horizontally and vertically, right? So we have a situation where we are both going to be moving away from the optical center horizontally and also vertically, right? That's going to be called combining prisms, right? And so if that's the case, you'll see the box here in the middle of the page, right? If given a lens that is decentered both horizontally and vertically, right, what you're going to do is Prentice's rule for each meridian, right? And then you're going to combine the two by doing vector addition. So let's go through an example of that. Example 5.16 here at the bottom of the page. What is a total prism that results from combining 2 base up and 1 base out, right? So here's our picture. I've drawn this up already, right? So we've got 1 base out here on the bottom, right? So 1 prism base out. We got 2 prism base up, and then the net prism is going to be what this resultant line is going to be from where we started with our first prism to where we ended with our second. And not to go too much into vector addition, but you guys remember that whenever we do vector addition, it's not going to be a boards question, but you add vectors head to tail, right? So we start with our first vector, and then we'd start with, at the head of the first vector, we go up with the second, and it's this dotted line, right? This dotted line is going to be our net prism whenever we go to combine the prisms, all right? Now, I think all of you guys can see that that's going to create a right triangle, right? And what's a key thing you guys remember about right triangles? There's a lot of different things, but I'm sure that geometry is coming into your mind. You're thinking of somebody's theorem, right? What theorem is it? Yeah, it's on the tip of your tongue. You're screaming at your computer now. Yeah, Pythagorean's theorem, right? So Pythagorean's theorem, right? A squared, right, plus B squared equals C squared, right? And so we're going to be able to use that to be able to answer this question, right? And so how are we going to do that? Let's talk about it. So working this problem out, we've got A squared plus B squared equals C squared. Whenever we go to square root that to get just C by itself, right, that's going to enable us to be able to solve this problem. So what I like to do is I actually substitute A and B for horizontal and vertical, right? So what we can do is we can think of the horizontal prism squared plus the vertical prism squared. That's going to give us our net prism whenever we're combining prisms, right? So this is the equation that I would suggest you guys memorize. Now in the book we have x squared and y squared, and I think that's a really good equation. It's essentially the same thing, but for me, I think it's a little bit easier to think of horizontal and vertical. So in my book, I just wrote out right next to example, or right next to equation 5.35, I wrote prism equals the square root of h squared plus v squared. That just helps me simply remember it's the horizontal prism plus the vertical prism. Whenever we work out in this problem, we take 1 squared plus 2 squared. That gives us 5. We square root that and we get 2.23 diopters as our answer. All right. Now you guys probably remember going through ophthalmic optics. You also can figure out what is the angle or what is the location of this vector, right, or this prism. Well, in terms of boards, you can't really answer this question without using sine squared or cosine, right? Not sine squared, but sine, cosine, or tangent, right? And so in this case, I think it's really going to be figuring out the magnitude of that prism, right? 2.23 diopters. I don't think necessarily that the angle is going to be something that is going to be asked, or otherwise you would have those functions on the calculator and they would be fair game to use. Let's finish up this section talking about vertical imbalance. So vertical imbalance is going to be due to the fact that you have different powers in the vertical meridian between the right and left lens. Okay? And the patient's going to be looking away from the optical center, either below or above the optical center. So what you're going to do in this, what you're going to do in vertical imbalance examples is you're going to do Prentice's rule for each eye, right? Once for the right eye, once for the left eye, right? Remember we wrote down the 4 different ways that Prentice's rule can be used, but different names, right? With vertical imbalance, we wrote 2 eyes next to that. So that's the key thing, is that it's 2 eyes. So once we get our answers for Prentice's rule, right, I think that's kind of the easier part, right? To me, at least, whenever it's hard in vertical imbalance, is trying to figure out, okay, now I've got the prism induced in the right eye, the prism induced in the left eye. How do I figure out the net imbalance, right? And so we put some rules in the book that I think are really going to be helpful for you guys. So let's go through those, and then we'll go through example 5.17. All right, so going through the rules, if you guys look, combining prisms over each eye to determine the imbalance. So for vertical prism, if the prism over the left and the right eyes are of the same direction, so they're both base up or both base down, right, you're going to subtract to get the net imbalance. All right? Now, if you're doing vertical prism and the prism in one eye is different than the other, so one eye is base down, the other one's base up, right? Well, now that's going to be moving the eyes in opposite directions, and so you're going to add to get your net imbalance, right? So the key take-home message that will summarize these 2 points is that with yoked prisms, you subtract to get the imbalance. So I would suggest writing that right above the box, right? So writing your text, with yoked prisms, subtract to get the imbalance. Now the same thing is going to be true for horizontal prism as well, right? So if you look in your text, if the prism over the right and left eyes are the same direction, so they're both base in or both base out, right? They're going to be moving the eyes in opposite directions, right? So base out prism is going to cause both eyes to converge, but they're going to be moving in opposite directions, right? Both are going to be moving in. And base in prism would cause both eyes to move out, right? You're going to be adding to get that net imbalance. However, if you have base out prism in the right eye and base in prism in the left eye, that's going to shift both eyes to the left, a yoked prism. So in that case, you're going to subtract to get your net imbalance. Great. Let's keep on going and talk about example 5.17. So a patient has a prescription calling for the right eye +5, the left eye +3. How much vertical imbalance is induced when the patient looks down 10 millimeters to read? So I'll pause the video, take a second to work it, and then we'll talk through the solution. So what'd you get for your final answer? 2 diopters base up prism in the right eye, or 2 diopters base down prism in the left. Excellent, right? So let's talk our way through this example, or talk our way through the solution. So we're going to do Prentice's rule, right? Once for each eye. So for the right eye, whenever we do Prentice's rule, we're going to get 5 diopters base up prism because we're looking below the optical center in a plus lens. And in the left eye, we're going to get 3 diopters of base up prism for our prism that's going to be induced. So we have 5 base up in the right, 3 base up in the left. Now we're going to be moving the eyes in the same direction, right? So we just talked about those rules. We're going to subtract to get our final answer. So we got 2 diopters. Now the trick is, does the base up stay with the right eye or go with the left? And the key is that if you're dealing with yoked prisms, right, and you're going to subtract to get your final answer, your base direction stays with the larger prism. So in this case, 5 is larger than 3, so the base up is going to stay with the 5 eye. You're going to get 2 base up in the right eye, or you can flip that and say 2 base down in the left. All right, guys, good job. Go dominate the quiz, and I'll see you on the next video.